Great, welcome back. So today we're going to be looking at oxidation states, or oxidation numbers as they're often called as well. So to kind of understand this a little bit, you can kind of read this first little paragraph here. We just talked about in atomic theory, when we actually have reactions, it involves a transfer of electrons. So of course we need to have one entity that loses the electrons and the other gains. And this is kind of easy to understand when we do like a lot of monoatomic ions. For example, like when we have magnesium solid going to magnesium 2+, right, we can easily tell it loses 2 electrons to kind of do that. And of course, it needs to actually come in contact with something in order to do this. Now, of course, as we've seen with a lot of larger or polyatomics, it gets a little more challenging to kind of keep everything in order, especially when we have to balance under acidic conditions. So this is where oxidation states kind of comes into play, and it's just like a little electron bookkeeping. So we kind of get to see where charges are coming and where they're going without actually having to balance full half reactions in order to do so. So of course, for atoms and molecules and polyatomic ions that share a pair of electrons in a covalent bond, we're going to assign the electrons to the more electronegative atom in the bond. So this is just not actually what happens, just as kind of how we figure out what the oxidation state is. So for example, if we look at water, right, and we know there's electrons right here inside these covalent bonds, and of course oxygen has 2 there. Now you can look up the electronegativities, but you know oxygen is more electronegative, and this kind of goes back to Chem 20 a little bit. So we know oxygen pulls the electrons towards itself, and why water is partially negative, where these oxygens are partially positive. So what oxidation states are saying is that what we're going to do is imagine that these electrons within the bond right here are transferred to that oxygen. So what we're left with is hydrogen, oxygen, and hydrogen, just like this. So this is where we kind of imagine that this is how water looks like. There's no bonds, you're just kind of attracted to each other, but oxygen gets that full 2- charge because it's taking the electrons, and the hydrogens lose them. So of course this we know doesn't actually happen, but this is where kind of oxidation states are just theoretical. So all oxidation state is, or oxidation number, is defined as the apparent charge that an atom would have if the electrons in the covalent bond belonged entirely on the more electronegative atom. So really what we're doing is the charge an atom would possess if it were ionic. Now we know these are covalent bonds, but this is just kind of, once again, it's more or less electron bookkeeping, just trying to figure out where the electrons are going. And for the most part, this is going to work perfectly with what we need it for. So an oxidation number, all this is just, well, it is a positive or negative number corresponding to the oxidation state assigned to the atom in the covalent bond. Now these do not correspond to actual charges. This is just the apparent. And really what we're going to be using these for is determine if a reaction is redox, determine oxidizing agents and reducing agents, and next lesson we're going to look at balancing redox reaction using oxidation numbers. But like I said, this isn't the actual charge, it's the apparent charge. So in order to kind of figure out these oxidation numbers, or the oxidation states, there are different categories of atoms or ions. So first of all elements are going to have an oxidation number of 0. So if you see something like a sodium element, the oxidation number is 0. A chlorine element, right, Cl2, oxidation number is still equal to 0, right? So they will have 0 charge because they're elements. Now if we have a monoatomic ion, remember monoatomic just means a one-atomed ion. The oxidation number is the charge on the ion. So for example, the sodium ion is a positive 1, so the oxidation number is also a positive 1. The sulfur ion is -2 charge, so the oxidation number is -2. Now, for hydrogen, because as you notice, there is a lot of hydrogen showing up in polyatomic ions, and of course in a lot of the reactions that we've done so far. So hydrogen, because it is kind of, as a non-metal, it's one of the lower electronegativity ones, and it's also higher in electronegativity than all metals. So we can definitely make an assumption about hydrogen, and that is all compounds except metallic hydrides is going to be positive 1. So for example, in HCl, because chlorine is going to be more electronegative, chlorine gets its charge, but hydrogen equals a positive 1. And then of course chlorine, these are two monatomic ions, is also going to equal negative 1. Now for our metallic hydrides, like lithium hydride, now in this case right here, lithium, hydrogen is a more electronegative atom, so it is going to get its charge. So it's going to take the electron, so lithium is going to be a positive 1. Also, it is a monoatomic ion, so that's why it's going to be positive 1. In this case here, hydrogen is going to equal negative 1. Now, oxygen, this is being one of the most electronegative atoms on the periodic table, except for fluorine. So this is why oxygen, we have our own little exceptions, or our own thing for oxygen as well. So oxygen in all compounds except for oxygens in peroxide. So in all compounds, it's going to be negative 2. In peroxides, is positive 1. So for example, in water, H2O, we know hydrogen is going to have a positive 1 oxidation state because of the rule up here, and oxygen is equal to negative 2. Now if we see a peroxide like H2O2, now hydrogen is still going to be a positive 1, but now oxygen turns into a negative 1. So this is kind of the only exception that you do have to be careful for, is when you do have a peroxide. Now last but not least, we have a rule for if we don't have, if you notice here, so if we have anything other than an element, monatomic ion, hydrogen, or oxygen. So for example, when we look at, phosphorus inside of this phosphate ion down here, we have no rules for phosphorus. So this is when we're going to use this rule right here. And this states that the sum of the oxidation numbers of all atoms are going to equal the net charge of the substance that's there. So for example, this is how we know when we look at magnesium oxide, it's MgO. These are two monoatomic ions, but we notice magnesium oxide doesn't have a charge. That's because the magnesium ion is 2+, and the oxygen ion from our rules up above is 2-. And when we look at, if we add these together, right, so just down here, positive 2 plus a negative 2 is equal to 0, and this is the overall charge on magnesium oxide. It's not charged. Now, as for our other one here, our phosphate ion, now in this one right here, phosphorus, we don't know, right? But oxygen, we know, has a negative 2 charge. Now, in order to figure out what phosphorus is going to be, we will need to use a little bit of algebra. And how this works, when we look at it, we have 1 phosphorus. So 1 phosphorus, plus now we have 4 oxygens, must equal the overall charge on our chemical species, which is negative 3. Now, when we do our algebra, 1 phosphorus plus 4, now the overall charge on oxygen is negative 2, because each oxygen is going to bring a negative 2 to the party. Now I'm just going to multiply this, so this is negative 8, right? 4 times negative 2 is negative 8. We bring it on the other side of the equation. It's going to turn into positive 8. So you got negative 3 plus 8. And what we're left with, I just kind of ran out of space right here, but algebra, if we do this, so 1 phosphorus is equal to negative 3 plus 8, and we get our phosphorus. Right now we can take out this question mark, because in order for algebraically this to work out, phosphorus must equal a positive 5. And that's kind of where we're going with all these here. So this rule right here will definitely come into play a lot for oxidation states, and how we solve them kind of algebraically will work out. All we need to do is remember is that the things that we have is elements are 0, always going to be true. Monatomic ions, charge on the ion, always true. Hydrogen, always going to be positive 1 except for the metallic hydrides. Oxygen is always going to be negative 2 except for when it's in peroxide. Other than that, we have to make sure that we can do this algebra step to kind of make sure the oxidation states all add up to equal the charge on the ion. So we are going to do some practice down here, and I'll go through the first few with you. So, of course, determine oxidation numbers, atoms, and compounds. we assign oxidation numbers to all known atoms, so the chart on the previous page. And then, of course, the sum or the addition of all the oxidation numbers must equal, in this case right here, it should be the overall charge. On the species, and of course we solve for any unknown oxidation numbers if we don't know what they are. And we're going to do that algebraically or mathematically. So our example right here, find the oxidation number for nitrogen in nitrate. So of course we know nitrate, this is a minus right here, so we don't know nitrogen because on the previous page there's nothing about the oxidation state of nitrogen. Now we know oxygen is always going to be -2. Now there are 3 of them, we're going to take that into our calculations, and the overall charge is -1. So algebraically we're going to figure this out. So we have 1 nitrogen, so that's nitrogen, plus we have 3 oxygens equals the overall charge of -1. So algebraically we got nitrogen plus 3, the oxidation state for oxygen is -2 is equal to -1. Right, so I don't have a lot of space to continue going down, so we just keep plugging in. So we start simplifying. Nitrogen plus 3 times -2 is -6, it's equal to -1. We're going to bring this over on that side right now. It's going to turn into a positive. Nitrogen is equal to -1 plus 6. Nitrogen, in this case right here, is going to equal a positive 5. Just like that. So all of them are going to be like this. Now normally as well, when you are solving them, it's only going to be one of the chemical species that's in there that you don't know the oxidation state. There's no way that you can solve algebraically if you don't know the oxidation state, if there's 2 in there that you don't know. So there should always be a case to solve them. So we have our examples right here. Now it would be a good idea to just kind of pause the video and try these right here. And if not, I'm going to go over this one, and we'll go this one, and let's go the potassium permanganate I'm going to go over. So pause. If not, just kind of fast forward a little bit and the answers will be there. But for those of you that just want to see a few more examples, so for this one right here, methane, so CH4, we have 1 carbon plus 4 hydrogens. The overall charge on methane, we see no charge up here, so that means the overall charge is 0 because it is a molecular compound. Now carbon plus the charge for hydrogen from our previous always a positive 1 is equal to 0. So carbon plus positive 4 is equal to 0. Carbon is equal to -4 when we solve. So that's how we get the carbon. All because we knew the oxidation state of our hydrogen. Now, like I said, for the carbon one right here, there's going to be 2, but when you do solve this right here, if you want, you're going to get carbon is equal to 0 in this example. So once again, just kind of work through that one, see if you can get it. But I kind of want to jump ahead to this potassium permanganate one, just because this one can be a little more challenging. So this one right here, what we have is potassium, we have permanganate, so MnO4-. Now the permanganate, the MnO4-, this is the polyatomic ion. But the potassium, this is by itself, this is a monoatomic ion. So we know the charge for that one. So algebraically we can set this one out. So 1 potassium plus 1 manganese plus 4 oxygens must equal 0. Now the charge for potassium, we know is positive 1 because it is a monatomic ion. Now that permanganate, MnO4- is the one that we don't know. So manganese we don't know. Oxygen is always -2. It's equal to 0. So in this case right here, we can start solving. So manganese is equal to, I'm just going to bring this one over here, so that's a -1, and also I'm going to simplify this and bring it over as well. 4 times -2 is -8. We bring that over, so we got 0 minus or plus a -1, and then we got plus 8, and we get manganese is equal to positive 7. And that's that. So for the other ones, once again, hopefully you got these down here, but you should get the chromium. Should be a positive 6. Sulfur. And should equal positive 6 when you get those done. And of course, if you had trouble getting those, just kind of fire me off an email. We can go through some of the other ones there as well. So this is going to show up in ways. So for example, this is an old diploma example where you have the oxidation number for sulfur in the following is blank. All right. So same thing using the algebraic steps. You should be able to go through here, but just make sure you circle if it's positive or negative, and I'm going to put the answers up in 3 seconds. And you get them something like this. So in SO2 it's positive 4, in SO3 it's positive 6, and H2SO4 positive 4, and H2SO4 should be positive 6. Hopefully if I did those out right. Now, last thing we do before we actually do this right here is basically kind of use the other things that I kind of mentioned. It's like not only just get the oxidation numbers, but kind of tell if we do have a redox reaction, and of course figure out oxidizing agents and reducing agents. That's the whole point of using these oxidation numbers. Now, because we're going to imagine that these oxidation numbers are very similar to charge, we're going to treat them the same way, and that means if we have an increase in oxidation number, it's the same thing as an increase in charge, like going from a 0 to a positive 6. Right? This just means it's an oxidation. And the chemical species is going to be a reducing agent. And same thing, a decrease in oxidation number, same thing as saying it's a decrease in charge, which is going to be a reduction, which means we're dealing with our oxidizing agent. Then, of course, if there's no change in oxidation number, it's not a redox reaction. So we have 2 examples right here of just trying to figure out, okay, we're just trying to figure out, all right, what's going to be the oxidizing agent, what is the reducing agent, what's being oxidized, what is being reduced. So when we're given something like this, it's very handy to write the oxidation numbers, just the common ones above all the things, and kind of highlight the ones that we don't know. So for example, the ones that we know, I'm going to write in blue, and the unknown ones that I have solved for is going to be in red. So hydrogen we know is always a positive 1. That's cool. Oxygen, this is an element, so 0. Carbon we don't know. Oxygen here is negative 2. Hydrogen, positive 1. Oxygen, negative 2. So the ones that we didn't know, of course, were our carbons. So when we solve these right here, methane we did on the previous page, we have a negative 4, and here it's going to be a positive 4 when you solve them out. Now, what we have is, we can see right here, our carbon is going from a negative 4 to a positive 4. Well, this is an increase, so which means this is an oxidation, which means our methane is our reducing agent. Now the other one that is changing, we can tell oxygen is going from a 0 to, we can use any one here, it doesn't matter whether it's this oxygen or this one right here, because they're the exact same oxidation number. We can see a decrease in oxidation number or a reduction. So that makes my oxygen right here my oxidizing agent, and boom. So basically, just by using oxidation numbers, we don't need to pull them apart and do half reactions, but we can figure out our oxidizing agent and our reducing agent based on just these ones right here. Now, there are a few examples on the next page. All right, but definitely this one right here, I want you to try to pause this one and see if you can get the next one just by oxidation numbers, and if not, well, the answer is going to go up in 3 seconds. So pause the video and try to get it. And we get something like this. So I didn't fill in all of them for these here, specifically the oxygen and the hydrogens, just because they're not changing. In this one right here, the chromium in our dichromate is a positive 6, and it's going to a positive 3, so there's of course a decrease or reduction, making the dichromate my oxidizing agent. And then of course the ethanol right here is going from negative 2 to a 0, or the carbon in ethanol is going from negative 2 to 0. Therefore the ethanol is my reducing agent, because negative 2 to 0 is an increase in oxidation number. And that's how we kind of solve those. Now if you're not sure where these numbers came from, once again, find me off an email, or you can save that for when we do our Thursday Google Meets, and we can go over that. Now last but not least, just for this lesson, is we do have a few old diploma examples right here, where we're using oxidation numbers to figure out which ones are being oxidized, which ones are reduced. Now you will notice for diploma example of the equations above, which ones are redox reactions are numbered. So you will notice with these here, there's no monoatomic ions, so like there's no metals and anything like that, so it's kind of hard to tell which ones are being oxidized and which ones are being reduced. But you do need to fill in all the numbers, and when you do get them right here, like you'll get good and kind of figure out which ones are which. You see elements right here, right? So 0 and 0, and hydrogen is +1, -1. So of course 1 is going to be a redox reaction, so we can kind of scratch out D. Now it's just a matter of figuring out which other ones are redox reactions or not. All right, and then of course your answer for this one right here, when you get going, you should get B. And last but not least, we have another one right here. So this one doesn't look like a typical redox reaction because we don't see any metals. This is a, once again, just kind of a reaction of all molecular compounds. So the only way to solve this is using oxidation numbers. Once again, if you want to pause this video and try to get the answer, please do. But when you are done, what you should get is the oxidation numbers for carbon dioxide, and this one right here, the carbon is going to be a +4. Sulfur right here is -2. Sulfur right here is 0. And then carbon in our glucose, I think in this one right here, is also 0. So we get carbon going from -4 to 0. Reduction, -2 to 0. Oxidation. And when we're answering the question during the reaction, we're using the hydrogen sulfide. So this one right here is the blank agent, and the sulfur undergoes a, well, we already saw right here, we know the sulfur undergoes an oxidation. So we know the answer is not B or D. And of course, because it's undergoing oxidation, it is definitely a reducing agent. So the answer should be A. And that is it. So next lesson, we're going to look at how to balance half reactions and reactions using oxidation numbers. And other than that, all right, see you guys for the next one.